Hello again. This is the second segment of section 3.3. Rather than having my usual sort of talky, I'm just going to go right back to where we were. The video is starting to get a little bit long, and I felt a little rushed. So I will just pick up right where we were before, section 3.3, page number 2. Now remember, we were talking about the unit circle. So I'll just kind of put that up here, unit circle. Remember, the unit circle is a circle that is positioned with its center coincident with the origin of the XY plane. And we use that as a framework to talk about different trigonometric functions of angles when they're measured in radians. So let me reconstruct the unit circle. Again, I'm going to try to make it fairly large. So we have our XY coordinate system, 1, -1, -1, 1. And I will try to superimpose that circle on top of these tick marks. Again, I'm not a great artist. I've never been very good at drawing decent circles. But there's kind of a smashed up version of one. Okay, and as you recall, we had put an angle also in standard position. So let me maybe pick a different angle just to illustrate the point. So I'm going to start with one that looks like it's a little bit less than a 45-degree angle. Okay, and just like before, I'm going to draw a right triangle. So the right triangle in this particular case is going to be horizontal. It's going to be perpendicular, or sorry, parallel to the XY axis, or sorry, the X axis. And so it'll be a right angle there. I'm going to label these points. Again, this was O, and continuing with the labels that I had before, I think I got up to D. So I'll now use E and F. And just like before, note that this length in here, because it's a unit circle, is a length of 1. Okay. So we talked about sine, cosine, tangent, and secant. Shockingly, we're going to talk about cotangent and cosecant now. So for this triangle, right? Remember, this is the angle, but because this is a transversal to a set of parallel lines, this is also that angle, right? Just the alternate interior angle theorem at play here. So I can talk about cotangent of this angle. Remember, that's going to be not opposite over adjacent, but actually adjacent over opposite. So cotangent of theta is adjacent over opposite, which happens to be the length of EF over the length of EO. And because EO is equal to 1, this reduces to EF. Now, you got to be a little careful because there are SIGN issues going on here, right? Cotangent is plus or minus, because a length is always a non-negative number, but cotangent in quadrant 1 happens to be equal to that length. But of course, we talked about that when we were talking about right triangle trigonometry, that the way to figure out the sines is kind of more of a trick more than anything. So in quadrant 1, at least, we can say that this length is cotangent. And so I want you to think about what happens. Notice that at an angle of just a little bit above 0, that this is really extraordinarily long, right? So it's basically comes screaming in from infinity, and as the angle decreases, or sorry, as the angle increases in quadrant 1, cotangent actually gets shorter and shorter and shorter. So cotangent is decreasing in quadrant 1. When you start thinking about what happens in quadrant 2, remember its SIGN is negative. So it's continuing to get more negative as the angle increases through quadrant 2 until as you get to close to an angle of pi, it becomes somewhat, well, infinite in length. So in quadrant 1 and 2, cotangent is decreasing. Consider down here in quadrant 3, note in quadrant 3, again, cotangent is positive. So geometrically speaking, it's the length of this, this line down here, which at just a little bit over pi is extraordinarily long in length. Positive, but becoming smaller all the time, which tells you that cotangent is decreasing in quadrant 3. And then flipping over to quadrant 4, again, this SIGN of cotangent is negative. Its value at 3 pi over 2 is 0, but it gets longer and longer and longer. However, the SIGN is negative, so it is still decreasing. So the bottom line is that cotangent is decreasing in quadrant 1, 2, 3, and 4. So cotangent is quite simply always a decreasing function. Compare that and contrast that with tangent, which is always an increasing function. So as you can imagine, cosecant is going to be related to this triangle again, as secant was in the previous example. So secant, looking again at that same triangle, or not secant, cosecant. Recall that cosecant is the reciprocal of sine, so it is the hypotenuse over the opposite. And if you look at this angle, the hypotenuse is FO, and the opposite is EO. So we have FO over EO. And again, just like with cotangent, EO is equal to 1. So we simply have that this is FO. So to draw it on the diagram, this is cosecant of theta. Right? This length. So as you can see, starting with an angle of 0, it would be infinite in length, but at any angle that's just a little shy or a little above, as theta increases through quadrant 1, cosecant is still positive, but it is decreasing in length until it reaches a value of 1. Now recall, cosecant is actually positive in quadrant 1, so in quadrant 2 as well. In quadrant 1, it's decreasing. In quadrant 2, it's actually increasing and is positive. So we would say that it goes from decreasing to increasing. Now in quadrant 3, the same sort of thing happens. Remember, cosecant is going to be negative in quadrant 3, so it starts off extraordinarily large but negative, then becomes a smaller negative number, which is the same thing as increasing. When it gets to quadrant 4, it's still negative, but it's becoming a larger negative number as the angle increases, which is the same thing as saying that it's decreasing. So in summary, we go from decreasing to increasing, increasing to decreasing. So quadrant 1, we're decreasing. Quadrant 2, increasing. Quadrant 3, increasing. Quadrant 4, decreasing, which is kind of an interesting sort of result. So that's, as I said, that sort of big picture idea is what we're going to talk about when we get into chapter 4. I just want you to kind of put that in your memory bank for a minute and think about that. So since this is kind of relatively short, I'm going to go into some sort of other kinds of applications that we can do using the unit circle, because for whatever, it's going to be like a left turn that I'm going to do here, because for whatever reason, it seems like this is a little bit of a challenge for folks. So just a totally separate idea. Let's consider points on the unit circle. So we're going to be talking about XY coordinates. So imagine, I'm going to do it a little bit smaller, but let's have a little unit circle over here, and let's consider, let's find a point. Okay, so let's do a couple of them. How about theta equal pi over 6, theta equal 2 pi over 3, and maybe one more. How about theta equal to 7 pi over 4. Okay, so that's an angle in quadrant 1 here. That's sort of number 1. This is an angle in quadrant 2. And this last one is actually an angle in quadrant 4. Okay, so the question that's being asked here is, what is the coordinate of this point? What is the coordinate of this point? What is the coordinate of this point? So it turns out that from this unit circle business, remember, if you look back at the one for the first one we did, notice that this point where the terminal ray of an angle crosses the unit circle, that's the coordinate we're talking about. And note that its x coordinate is cosine and its y coordinate is sine. So, I mean, this is really kind of a trivial sort of problem, because if you want to know the coordinate based on the coordinate on the unit circle based on the angle, it's just simply the x coordinate is the cosine and the y coordinate is the sine. So this corresponds to the coordinate, well, cosine of pi over 6 is square root of 3 over 2, and the sine of pi over 6 is 1/2. So that's the coordinate that's associated with the terminal ray of an angle whose measure is pi over 6 radians. Similarly, with 2 pi over 3, remember 2/3 pi, that's reference angle is 60 degrees. So sine is positive. Sine of 60 degrees is 1/2. Oh, sorry, root 3 over 2. And cosine is negative. Cosine of 60 degrees is 1/2, so negative 1/2. I've got this totally backwards. Sorry, it's negative 1/2 cosine sine. So negative 1/2 square root of 3 over 2 positive. Okay. Finally, for angle in quadrant 4, remember that both that sine will be negative, cosine will be positive. And this is the reference angle 45 degrees, pi over 4, 45 degrees. So we will have cosine is positive, and it is square root of 2 over 2. Sine is negative. Again, the reference angle tells you its value is root 2 over 2, but we have a negative sign. And so here we have the coordinates along the coordinates on the unit circle at specific reference or specific angles. And like I said, I'm not really sure why this transition is so challenging, but for some reason, students sometimes find that a little bit hard to figure out. There are some other problems, and I don't want to make it too explicit exactly how this is supposed to work, because I'd like you to struggle with it a little bit just to kind of think about what exactly is going on. But the rest of the section talks about range and domain and just some stuff that seems kind of unnecessarily complicated. The big takeaway is to think about this. I mean, it's kind of strangely placed in the chapter too. You'd think you'd want to start with this, and many trigonometric textbooks never even talk about degree angles. They just start with this unit circle thing and then move from there. But I don't think that that's necessarily the best way to go. Anyways, so this I don't think that there's really much more to talk about in terms of section 3.3. There are some practice problems. the more interesting applications actually come in 3.4 and 3.5 that have very little to do with this unit circle. Okay, well, that being said, I'm going to sign off here, and I will see you in the next section.